between single crystal, polycrystalline, and amorphous materials, and talk about how the structure of matter affects its physical properties. Okay, let's talk about single crystals first. What is a single crystal? A single crystal is a material in which the crystal lattice is continuous throughout. That is, the orientation of lattice vectors in one part of the material is exactly identical to the orientation of the lattice vectors in any other part of the material. Another way to think about this is that I could take a unit cell in some area, and I could, by translating by an integral number of lattice vectors, map out the atoms in some other area of that material. So continuous crystal lattice. Okay, so you might be thinking single crystals are kind of weird, they're an oddity. We don't really deal with them very much, and that's not necessarily true. In fact, just about every bit of computing technology that we deal with and carry around in our pockets in a cell phone, for example, is built off of silicon. And so what people do is they take very large single crystals of silicon, and that's called a boule. It's grown by a starting seed, and it gets larger and larger until it gets to some diameter. But all of this, again, is a single crystal of silicon. And then we take it and we dice it into very, very thin wafers, and we deposit things and we do photolithography on top of that. But the starting block for all of this computing technology, for almost all of the devices that we carry around with us, is single crystal silicon. So it's a very important thing to understand. So let's talk about our physical properties of the single crystal substance. So maybe I want to talk about electrical transport. Maybe I want to talk about the elastic modulus of material. It doesn't necessarily matter. The important thing is to think about how those atoms are oriented in one direction relative to another. So we talked about linear density before. That's one good example. The linear density, so I'm looking at a simple cubic crystal here. The linear density in the 100 direction is not the same as the linear density in, say, the 110 direction. So the atoms are a little bit spaced further apart. The electronic orbitals aren't overlapping as much as they are in the 100 direction. And so it makes sense that the physical properties in these two directions are different. And what we say then is that they are anisotropic. So that means not the same, essentially. So an anisotropic material is a material in which if I measure the physical properties in one direction, they're not necessarily the same as if I measure them in some other direction. And any single crystal that we look at is going to be anisotropic. Let's think about one example that you're all familiar with. That's graphite, which is what is used in pencils in place of lead now. And we think about graphite as a very, very soft material. And indeed, that's true. If I write with my pencil on a piece of paper, some of that graphite gets left behind. So if we look at the crystal structure of graphite, we actually see sheets of hexagonal carbon. They're very strongly bonded together, and they're weakly bonded to sheets above and below them. And so what that means is that the bonding strength in this direction is very, very weak. And when I write, I'm liable to flake off little sheets of graphite, and that's why I leave behind a black line when I'm writing with a pencil. But it's important to note that the bonding in the plane is very, very strong. One single sheet of graphite is what we refer to as graphene, and the strength per weight of that material is stronger even than something like steel. So this is one of the strongest materials we know. So this is a great example of something that is very anisotropic. The crystal structure is anisotropic, and that means that the physical properties are anisotropic. One other point that's worth bringing up is that if I look at the properties in one direction, say the 100, and I look at the properties in another direction that's related by symmetry, say the 010 direction, if these two directions are symmetrically equivalent, then I would expect the properties to be identical. So that is, if I took a single crystal that happened to be cubic, and I measured, say, its elastic modulus in the 100 direction, and I measured it again in the 010 direction, I know these two directions are symmetrically equivalent. And that means that the properties are also going to be equivalent to those two directions. So this is a very important lesson to learn, and that is the symmetry of the properties of material is related to the symmetry of the crystal structure. Okay, we talked about single crystals some, but many of the materials that surround us and that we interact with on a daily basis are actually polycrystalline. And what that means is that they're made up of an assemblage of individual single crystals. So this is one grain, and this might be a single crystal that has some particular orientation. And then there's a neighboring grain next to it. And so this also has some orientation, but it's not necessarily related to the grain next to it. It is definitely not identical. And so I can keep doing this, and each grain is liable to have its own particular orientation. Now, if I look at the boundary between two grains, this is what we call a grain boundary. And I look at it at a very, very small scale, then I might see something like this. This is a transmission electron microscopy image of a grain boundary. So I see one crystal lattice over here, and I see another crystal lattice over here. And I can see that they're at different orientations. They're different orientations than the neighboring grain. Right along here is the grain boundary. And so what has been observed is that atoms tend to configure themselves to take the lowest energy configurations along those grain boundaries. So oftentimes we see repeating units that are periodic along that grain boundary. Okay, this is a polycrystalline material. What's an example? Well, I'm sure when all of you go back to your dorm rooms this evening and go into the bathroom, you'll see lovely granite countertops. This is a great example of a polycrystalline material because it's very visible and you can see it with the naked eye. So in something like granite, you actually have two types of feldspar, this pinkish material and this milky whitish material. So those are two different phases. We have quartz, that's the kind of gray colored material. And then we have biotite, which is a kind of mica, that's the black material. So we actually have four different phases. But even more than that, each individual crystal has its own orientation with respect to each other. So I can look at this grain of feldspar, maybe it's oriented this way, and I have some quartz here, it's oriented in a different direction, and then we're back to feldspar over here, some other orientation. So this is an example of a polycrystalline material that's made up of a large assemblage of single crystals. Like I said, this is a fairly intuitive example because it's something we can see with our naked eye. Many other materials, for example, a lot of metals also are polycrystalline, but you can't. The grains are small enough that you can't necessarily visualize them with your naked eye. Okay, now let's talk about the physical properties of polycrystalline materials. Remember, each one of these is an anisotropic single crystal. So the properties in some direction are not necessarily the same as the properties in some other direction. But remember, in a randomly oriented polycrystalline material, the neighboring grain has a different orientation, and therefore the properties are not necessarily consistent throughout the material. And if I take an average of enough randomly oriented grains, what I'll see is that the properties are going to be independent of direction. Now this makes sense, right? Because I'm taking a lot of things that each have anisotropic properties. I'm randomly mixing them up. So if I measure across large enough length scale, say the elastic modulus, really it's going to be the average of all of these individually oriented single crystals along that direction. So this is what we call an isotropic material. So the properties are the same regardless of what direction that we're measuring them in. Now, you'll notice that I kept saying randomly oriented polycrystalline material. And that's very important because when we do things to materials to physically manipulate them, oftentimes we lose that random orientation. So, for example, if I take a sheet of metal and I cold roll it, so I'm going from a larger cross-section down to a thinner cross-section, in that process, I'm going to orient the crystals. So whereas before, I had a bunch of randomly oriented crystals, now they're kind of going to tend to align in some particular direction. So this is what we call preferred orientation or textured materials. Now, if I measure the properties, again, in the part that's randomly oriented, they're going to be isotropic. It doesn't matter which direction I measure them, they're going to be constant the same. But if I come over here to the part that is textured and I measure the physical properties, say, again, the elastic modulus, now I'm going to find that the elastic modulus is going to depend on the direction I measure it in. And that's because I've sort of started to orient these, so they're kind of coming back to some intermediate between the random polycrystalline case and